Okay, so it's my pleasure to introduce Rasul Shafikov on polynomial and rational convexity of singular real submanifolds.
Thank you. I'm very happy to be back to Stony Brook after 12 years, and I'm grateful to Denny Hill and Eric Bedford for making this happen. My talk will be around one particular application on approximation of continuous functions on compact surfaces. And let me start with a basic example, so a baby example, model example. Let's take S1 inside C. So it's just a regular unit circle inside C, and we know that if I take rational functions with poles of S1, and if I take the closure of this set in the topology of uniform convergence on S1, then this will be dense, or the closure will be the set of all continuous complex valued functions on S1. And the way I want to think about this is the following. I want to think of S1 as being an abstract, compact, one-dimensional manifold, and I want to think of the map e to the I theta as an embedding of S1 into C. So theta is a parameter here, parameterization of S1. And I want to think of this result in the following way. I want to think of this as saying that if I take functions of, if I fix a particular function on S1, e to the I theta, and I take rational combinations of this just one function defined on S1, and take the closure of this, again, in the convergence of, uniform convergence on the whole S1, then I get all continuous functions on S1. And then in this formulations, it's easy to formulate a more general question. Suppose I have a compact, real, compact manifold, and I want to say, to ask whether there is some collection of functions so that when I take the rational combinations, take the closure, I get the set of all continuous functions of this. So specifically, I will be interested in compact surfaces. So my question is, what about surfaces? And well, the main idea would be the following idea. Is just to mimic what happens with a circle. We'll just take find an embedding let's say F with components F1, F2 of my surface S into C2, so that on the set f of S, I can approximate any continuous function by rational functions on C2, so that on f of S, any continuous function can be approximated by rational functions. Then I can say that continuous functions on S have a well-defined structure. I take rational functions of these two functions, the components F1 and F2, and I take rational combinations with poles of f of S, take the closure, and I will have something. I will have the approximation result for all continuous functions.
So S is always a compact surface in this?
Compact, yes.
But not necessarily oriented.
Not necessarily oriented, yes. Okay, so taking this as the main idea in answering this question for surfaces, well, this, of course, you can do the same thing for arbitrary compact manifolds, but the answer that I have right now is for surfaces only. So to say something more about this, I have to give a couple of definitions from complex analysis. And I'm going to start with polynomial convexity.
So in the higher dimensions, you take an n manifold and embed it in Cn.
Yes. Yes.
So we can embed it in Cn.
Into Cn, yes. So the expectation is that you need at least as many functions as the real dimension of the manifold that you want.
If this can be done, can it always be done with f real analytic?
You mean the embedding function or something?
Yeah, the embedding function.
The answer that I have for surfaces, there it will not be real analytic, it will be only smooth. These are fine. But we will see later why they are not real analytic. Okay, so polynomial convexity. So I start with a compact set in Cn. And I say that X is polynomially convex if what I want to find a polynomially convex hull first, so these are such a point Z in Cn, such that P of Z in absolute value is less than or equal to the norm of P on K, the subnorm, where P is a holomorphic polynomial. So this is called a polynomially convex hull of X, and X is,
So K is X.
sorry, not K, X. So X is called polynomially convex if X hat is equal to X. Well, if we take C, for example, n equal to 1, and if I take any compact set that has a real hole in it, or some hole, then by the maximum principle, any polynomial, the value inside this hole will not exceed in absolute value the value on this compact set X. So clearly, this whole thing has to be in the polynomial convex hull of X. And that's the complete description of a polynomial convex hull in one variable. So X is polynomially convex if and only if the complement has no boundary component. But in high dimensions, there is no simple description of a polynomially convex set. And even if you take curves, some of them may be compact curves, some of them may be polynomially convex. So they're either polynomially convex or they may be boundaries of what is called a holomorphic disk. So it's just the image of the standard unit disk under a holomorphic map, which is continuous up to the boundary f, and then this f of S1, this curve, again, by the simple application of the maximum principle, its hull is going to be this whole thing, the image of. So if I take the hull, this is going to be f of the disk. This pretty much answers everything about the curves, at least in the simple case. But for even for more complicated compact sets, it's really difficult to verify whether it's polynomially convex or not. Although there are certain certain characterizations of polynomially convex sets. that's right. And the second technical definition that I'd like, sorry, let me just maybe say a few more things. Now, if I take S to be a surface, let's just stick to dimension 2, in C2 surface, compact, then it's actually known that S is not a polynomial convex. There is some topological abstractions that prevent S from being polynomial convex. And on the other hand, if S is totally real, that means if we look at the tangents plane to S, and it's not a complex tangent, it's not a complex subspace of C2, then this S is called totally real, and then you can say that totally real surfaces are always locally polynomially convex. So near every point there is a neighborhood basis of polynomially convex compact sets, but globally they're not polynomial convex in general.
So does your surface need to be orientable there?
No, it's any topological embedding of a surface. And this is true for any dimension. If you take Cn and if you take any topological compact submanifold of real dimension n, then it is never polynomially convex. And the second definition is of rational convexity. So X in Cn is rational convex.
Does the argument involve finding a homomorphic disk that has boundary on S, or?
Yeah, it's an interesting question. So one may wonder if the hull will necessarily contain a holomorphic disk similar to a circle. And that was what people was wondering about in the 50s and in the 60s until they found a counterexample that there are compact sets which are not polynomially convex, so there is a non-trivial hull, but it doesn't contain any holomorphic disk. So what they say in these results that there's no analytic structure in the hull. Yeah, you may wonder whether maybe if you have a nice surface, like a smooth surface, totally real surface, maybe those ones would have always a disk attached to it. So to answer that question, if S was a Lagrangian compact, it's a manifold, then Gromov's theorem says that there is always a disk attached to it. So it's a famous Gromov's theorem about attaching a holomorphic disk to a compact Lagrangian surface. But then later on they found, I think Alexandra and Duval found examples of totally real, but not Lagrangian compact surfaces. They are not polynomially convex, and there is no disk attached. Okay, so the second notion is that of rational convexity. So a compact set X is rationally convex if for any point Z which is not an X, there is an algebraic, so complex algebraic hypersurface let's say pi, such that pi passes through Z, but pi intersecting X is empty. So here's a compact set somehow, and there is a point Z, and then there is a complex hypersurface algebraic which completely avoids X and passes through Z. And if such pi can be found for any Z outside X, then X is called rationally convex. And then again, in one variable, it's easy to, in one variable, a complex hypersurface is a point. Therefore, it's immediate that any compact set in one variable is rationally convex. But in higher dimensions, again, it's not an easy problem to determine whether a given compact set is rationally convex. So why these?
So the term rational here is puzzling. So this hypersurface could be just complex analytic. It doesn't have to be given by. It's not anything algebraic.
Well, in a definition, it is algebraic, so it's a zero set of polynomial.
Oh, it's algebraic. Algebraic. Yeah, I see. Yeah.
You can also give definition in the spirit of the how. So you replace P by rational functions, and you get the how. And it will be exactly the same definition. They're equivalent.
What if you replace complex algebraic by closed complex analytic?
It would be the same, then you would just simply approximate your, if this is given by a zero set of an entire function, you will just approximate it somehow with
As long as the set you're looking at is compact.
this set, that's, yeah, well, definition, this
The
is
compact
is always compact.
compact closure.
So why these definitions and why do we need this in this type of equation? For a simple reason, which is called Oka-Weil theorem, or Oka-Weil type theorem.
They.
Or Weil.
They.
Okay. Oka-Weil.
The eldest sign.
Which says the following, that if x is rationally, polynomially, or rationally convex, then any function holomorphic on x, the x is a compact set. So holomorphic means holomorphic in a neighborhood. Can be approximated uniformly on x by holomorphic polynomials in the case of polynomial convexity or rational convexity. In the case of rational convexity. So going back to our strategy, if we have a compact surface and we want to find some rational combination, maybe polynomial combination of particular functions, which will be the components of the embedding, then the image of this embedding must be rationally convex and polynomial convex. The converse is also true. If you have such approximation, then your set has to be polynomially convex or respectively rationally convex. So therefore, the conclusion from this is that by looking at this f from S into C2, we want f of S to be rational convex. And it's immediately okay, again, we can say that we cannot hope to have polynomial convexity here, so because of that result. So that means that the sort of polynomial combinations of any two functions can never be dense in the space of continuous functions. So it's only rational combinations that may be dense. Okay, so we need to look at submanifolds which are rational convex. And here is a result which is due to Rasul which gives a complete characterization of compact surfaces, or in general submanifolds that are rational convex. So it's a theorem to Duval and Stony. And it says the following, that suppose that S, and I'll write it in full generality, so is a compact submanifold of Cn, so it's smooth, totally real. So that means that dimension of S is at most, real dimension is at most, it could be less. Then we say that S, well then the theorem is that S is rationally convex only if S is Lagrangian, sorry, isotropic with respect to some scalar form omega. So in particular, in the case we're interested, so S as a surface in C2 has to be random. And then this condition that it's just some scalar form is not really any different. We are not interested in specific embedding of S. We just want to have some embedding which is rational convex. So we have the choice of omega, and in fact, if you can do it for some omega, then you can do it for the standard symplectic or scalar form on C2. So there is no loss of generality to say that it has to be Lagrangian in C2 with respect to the standard symplectic or scalar form on C2. So the next question is then, well, when can I have such an embedding? And the simplest topological abstraction is a result due to Arnold, which says that, well, to be specific for our situation, I can simply say that S, the early characteristic of S has to be 0 if S in C2 is Lagrangian. And it has to be 0 mod 2 if S is non-oriented. So, well, if we take then orientable case, that means that so only the torus has Lagrangian embedding into C2 for, you know, among all orientable surfaces. And there is a result due to given time. And this is a trivial. You just take the standard torus S1 cross S1, and that's already Lagrangian in the standard C2. So there's nothing to do for the torus. But Giventhal showed that actually, if you take non-orientable surface, so if S is non-orientable, and the early characteristic of S is 0 mod 4, and it's negative, then S has embedding, has Lagrangian embedding, smooth Lagrangian embedding. Because this is just a necessary condition, it's not a sufficient condition for the embedding to exist. And then there is also a difficult case when S is equal to the early characteristic is 0, so that's the Klein model, and that was settled by Shevchishin not long ago, about 7 or 8 years ago, and the answer is no. Klein model does not have a smooth Lagrangian embedding into C2. So the Klein model, the answer is no. Okay, so that it may seem that we cannot continue with this program of Lagrangian embedding, but there is another result which is also due to Giventhal, which says the following. So that's 1986 or 87. So first, let me introduce a special map which is called open with umbrella. So
just to get straight, what you've done so far, that was just, he was just putting in basically an artificial condition that you had such an object which was totally real, but a priori it might not be.
A priori it might not be, yes. Yes. At the end of the day, this will work out nicely. And it seems that even if you introduce complex points, it's not clear whether you're going to get better result or not. Yes, but it is true that here we assume that it's totally real. Okay, so open with the umbrella is a special map called pi from R2 with variables T and S into C2. And the variables here are going to be x plus iy, u plus iv. So maybe this is z and this is w. And it's an algebraic map. So T S goes into T squared, 2/3 T cubed, TS. T squared and then S. This is X, this is U, this is Y, and this is. And it's an interesting map because pi, and everything is so this is a local consideration in the neighborhood of the origin on R2. So pi is a homomorphism. It is smooth everywhere, of course. Smooth diffeomorphism away from zero. And if I take
Can you smooth embedding? Emotion embedding?
onto its input, yes. It's a local embedding. And the pullback of the standard symplectic for this zero. So it is a topological embedding, which is a Lagrangian embedding except for one point. And we consider this map pi, and then this will be, let me call it sigma, which is the image of R2 inside C2. And then we're going to take phi an arbitrary symplectic morphism. And then we're going to take phi of sigma inside C2. So this will be called open loop umbrella. And maybe I'll call the standard open. So this is a very specific map, degree 3 algebraic map. And this is just a arbitrary local symplectomorphism. Let's say phi of 0 is equal to 0, but it doesn't have to. And the result by given tau is the following, that any compact surface S admits a map F from S into C2, which is a local Lagrangian embedding except a finite number of singular points. And the points are of two types. Is either transverse double self-intersections, so I'll just call them double points, this transfers into section like this, or these are open Whitney umbrellas. And there is more. These are open Whitney umbrellas are stable under perturbations that preserve the properties that are needed, and they form an open set. In fact, would be even generic. But the point is that this is true for any compact surface. And I will call them, following Arnold again, Lagrangian inclusions. So these are not embeddings, these are not immersions, because at the umbrella here, the rank of the map is 1 and 0, so it's not an immersion. So it's, well, Arnold calls them inclusions. And moreover, there is a topological formula that connects the early characteristic of the surface with a number of singular points that you can have. So let me write them down. So in the orientable case, the formula is minus chi s plus 2 times d minus m is equal to 0. So d is the number of double points, and m is the number of umbrellas. So this is the number. And again, this is a necessary condition. So in other words, if you have a Lagrangian inclusion, then the number of double points, number of umbrellas, and the early characteristic must satisfy this condition. And it is observation of Holden is that in fact any combination of D and M for which this formula holds is achievable. So you can have a Lagrangian inclusion with this number of D and M. So any D and M are okay. In particular, we can take D equals 0 and take M to be minus the early characteristic. So that will work for all surfaces except the sphere, which has positive early characteristic. And you can have a Lagrangian embedding without double points. You can only have Whitney umbrellas. Therefore, any orientable surface except S2 has, or admits, a singular, well, a Lagrangian inclusion with umbrellas only. And this is important because double points are not good for the approximation problem. If there are 2 points on the surface which are mapped to the same point in the image, it's hard to expect approximation because your continuous function will take different values, and any function defined on the image will have the same value at this point. So approximation in general will not be possible. And the non-orientable case the formula is the following. So we take the early characteristic plus 2 times d minus m is equal to 0, and this is mod 4, which is also due to order. And again, here this is a necessary condition that connects D, M, and chi. And this is a recent result due to Nemirovsky. then Ziegel, which says that, well, they have a precise formula for admissible D and M, but I'll just formulate the result, which is which we will gonna need. So we can take for any surface non-orientable, we can take except RP2, we can take D is equal to 0. So for example, for the Grand model, we know that we cannot have a smooth embedding, but we can have embedding with M equal to 4 and D is equal to 0. So there is, so there is an embedding which is Lagrangian except 4 points which are umbrellas. Okay, and the sphere here is the easiest thing that you can do is to have what is called Whitney umbrella. So it's a map of T as tau, and then you will map it into T plus, this is in F3, T plus I T tau, S plus I S tau. So this is if I call this map phi, this is P of S in C2. So this is a Lagrangian immersion of a sphere with one double point. Okay, and here RP2 can have, we can take M equal 1 and D equal to 2. And then we can have a Lagrangian embedding of RP2 with one umbrella and two double points.
Is there a particular reason why in the non-orientable case you don't have a minus sign in front of the Euler fixed it? Is that just a
well, you can have a minus sign, but then your formula will be a little bit different. I don't know if it's possible to combine these two together, but they seem to be a bit different.
Do you have a high-dimensional analog of this?
This one. Well, it's a good question. The point is that these open Whitney umbrellas are defined only in C2, the way these are defined. There are some analogs of this considered by Ishikawa in high dimensions. But I don't know any result that will say that there is for certain class of compact manifolds of certain dimension, you can always have an embedding with only this type of singularities. That I simply don't know. Okay, so now I like to formulate some results that give the answer to this approximation problem. The first result is due to Sukhov and myself, and also by Mitra and myself as my PhD student. The following: that any open Whitney umbrella is locally polynomially convex. So that doesn't really answer any of the questions about the approximation.
So this is in the context of you're given one of these Lagrangian inclusions of a compact surface.
No, this is local question. So we start with a map like this, and we take an arbitrary symplectomorphism, and we look at this set. So this is in C2 looks like this. So this has just one isolated singularity. And outside, it's just a smooth Lagrangian surface in situ. And this result says that there is a polynomial convex neighborhood basis on this point in this view of C. It's a local result.
So I see, so it's saying that that's looks like your local model up to symplectic morphisms. You moved the standard, you wrote down a specific model you called the open with.
Yes, so that's.
And now
that's
you move it by symplectic morphism.
And then you apply symplectic morphism. But even for this, the standard umbrella, the one that is given by specific formula, the question of local polynomial convexity was not clear. In fact, essentially the same proof that we do for the general one. That's the only proof that I know for the standard umbrella as well. Yeah, but the sort of, it's more interesting to consider this class of umbrellas because this symplectic morphism, it doesn't preserve complex structure. So it doesn't preserve, seemingly doesn't preserve polynomial convexity. But at the end of the day, somehow, they all, still all of them are local polynomial convexity. And the reason why I mentioned that is that this is the main tool in the next theorem, the formula. Just need to also myself. And let me just take a couple of statements. Some of them are simple, but nevertheless. So first of all, we can, there's for any surface S, we can find a Lagrangian inclusion with only standard open loop umbrellas. So which look like this, and maybe we can just translate and rotate things like that. Simple linear maps that do not change polynomial convexity. So those ones are allowed. And if you have, so we know that there is always some Lagrangian inclusion. And the first little result is that in this case you can always modify your Lagrangian inclusion so that umbrellas.
Any surface here, so any compact surface?
Any compact surface, yes.
Any compact? What about the two-sphere?
Sorry?
So the two-sphere you need a double point. So
yeah. So we're not saying that there are no double points. We're saying that
for which the umbrellas are all standard.
Yeah, the umbrellas are all standard. If there are double points, they're going to be double points. And the second part is the most relevant. Is that
And this is with any fixed number of double points that's allowed?
any finite number of double points and any finite number of umbrellas. So that is okay. And the second part is that any Lagrangian inclusion with standard open loop umbrellas is rational convex. And therefore, as a corollary, we can just take the Lagrangian inclusion for all surfaces except S2 and RP2. We take Lagrangian inclusion which does not have double points. And then umbrellas we can modify to be standard umbrellas.
So the statement here is Lagrangian inclusion without double points and with standard open?
No. This is general, including double points.
So you were saying before that that was sort of a hard point on approximation, but you
No, we're not. See, this has nothing to do with
Oh, I see.
approximation. This is only about rational convexity as a compact set. As a compact set, it is rationally convex. And then the approximation, the corollary about approximation will be here. And there we need to take, so if S is not equal to S2 and is not RP2, then we can have Lagrangian inclusion without double points. We can modify this inclusion so that the umbrellas are standard. And then this modified inclusion, the image is going to be rationally convex. And there you can do approximation. So when I cited Oka-Vail theorem, there I said holomorphic functions in a neighborhood of compact set can be approximated by rational functions. So you need actually extra work to say that continuous functions on your compact set can be approximated by rational functions. But I'm going to suppress this technical detail and simply say then there exist functions f1 and f2 from S into C2 such that rational combinations of these two functions are dense and C0 dense. And it seems that this S2 and P2 are really the exceptions. They don't come from the method. Although I don't know. So it's an open question whether you can do some other kind of embedding that will be rationally convex. And so therefore you will still have these two functions. But it seems that these are really exceptions. They simply have somehow more continuous functions than the combinations of any rational combinations of any two fixed functions.
So in the construction, this F is a topological embedding, but not a smooth embedding.
Yeah,
But if you now just approximate by smooth embeddings, you're going to lose Lagrangian. This sounds like this polynomial its density should be still true, right? You take, if
so these maps, the image is not smooth, but these umbrellas they're smooth. The maps themselves are smooth.
Right.
So F1 and F2 are smooth.
So I was asking a slightly different question. So now, I mean, this thing is not, for example, a smooth embedding. But what if you were just to now take a sequence of smooth embeddings that converge to this? Might you still, I mean, so you'll lose the Lagrangian property for those, but you still might be able to prove that you still get density just by you're looking at rational combinations of these functions and you approximate the functions.
But what are these functions that you? Oh, no. But then it may not be true that the sequence that you produce is the sequence of rational functions. So their rational functions may not be dense. You can yes. So these umbrellas are there locally graphs, and you can approximate them by something smooth. But whether these are rational convex and what are the density properties of this smooth submanifold with which you approximate, I'm not sure how this works exactly.
Yeah, well, I was thinking that you might just be able to do it directly by suitable estimates. That maybe if you had an embedding that was sufficiently close to an embedding like this. So I mean, you've used a lot of techniques coming from the theory of the Lagrangian submanifolds and so forth. But the question does not clearly hinge on that. You might be able to get some.
Exactly. The question is very general. You just your surface is not even in space. There is no embedding right in the problem. It's true. Maybe there is a better way to do it, and maybe you get a better result. But that's the approach that I know. It seemed to work, but I don't know what you think. I don't know any other approach that actually gives the results. Maybe you can approximate this by something smooth, then the rational sets, they're not sort of dense, or sort of they don't usually, property of being rationally convex is not stable under small perturbations and things like that. So this is a very delicate sort of property that will be difficult to control here in general. Okay. And one just curiosity about the sphere, if you take S2, then Okay, so there is no way to embed this as a Lagrangian submanifold in C2. The best we can do is this Whitney umbrella. But we also know that if we have a continuous function into C or R2, then by Bar-Coulomb theorem, there are two antipodal points where this function attains the same value. And so if you rotate them, if you do a rotation of the sphere and take this to the North Pole and to the South Pole, then this Whitney umbrella, so the Whitney sphere takes the sphere, and then these 2 points are the double points. So if you start with an arbitrary continuous function, there are 2 antipodal points where this function attains the same value. So you translate, make a North Pole, South Pole, and then you use the components of this Whitney embedding of the sphere, and then you have approximation. So, so if you take continuous function and do approximation, or if you take rational combinations and rotations of the sphere, then you have actually the space of all continuous functions. And with RP2, we can do something similar, but it doesn't sound very great. So in this result about rational convexity, this is the main tool to show that it's local polynomial convexity. This local polynomial convexity gives you pluriself-harmonic functions, I'll just say for a few words, with certain properties. And these pluriself-harmonic functions crucially improve rational convexity because by Duval-Ciccone, you want to have some Kähler form which vanishes on your set. And this pluriself-harmonic function that comes from polynomial convexity would be the Kähler potential that you want to construct so that you get rational convex. So these 2 problems are related to each other. And well, I think a big open question is what happens in high dimensions. Suppose you have 3-dimensional manifolds and you look at the space of continuous functions there. Is it possible to find 3 functions, for example, so that the rational combinations of that's there? I think that's an interesting question, and I don't know how to start to try to prove this. And one also observation, so that rational convexity, so polynomial convexity cannot be here, so you cannot have polynomial combinations. So somehow rational combination is the right class of functions. Thank you.
So I asked this question about real analyticity before. So I was missing this point, crucial point, that you're looking at maps which are not actually smooth embeddings, but they actually are smooth. They're simply fail to be embeddings.
Yes.
Can these always be chosen to be real analytic? Or you have to use different techniques to construct the.
Well, for our proof, we rely. So this is algebraic, I guess. I don't know. I sort of, my feeling is that you cannot, in general, expect them to be real analytic. I can't give you exact argument why they cannot be real. So my feeling is that it's not possible.
So certainly your standard models are
given the
algebraic things, and I mean you can't use partitions of unity, but there are very good. I mean these are sheaves without any higher cohomology, basically sheaves.
Yeah,
so you can actually get around having these partitions of unity.
Right. Yeah. So you can put some real analytic structure on your surface, and then I don't know. I think when you have already 2 umbrellas, somehow you have something real analytic or algebraic here, real algebraic here, and just to make them match together, that's already seems like a